last lecture we actually got to see what the basic definition of classical field theory was. We saw that it was just the classical mechanics of fields, and one might guess that the natural thing to do would be to actually go ahead and start discussing how to write actions or Lagrangians for fields, but we will hold that back a little bit, because there is something which we need to input or understand, is how symmetry in nature occurs in nature and how best we should formulate it. So, the next 3 to 4 lectures will be a sort of introduction to symmetry, group theory, etc., sort of a mathematical background or prelude before we actually start doing classical field theory. And it is actually a very important ingredient for what we will be discussing in this course, because as you will see that symmetry is something which is sort of an underlying principle. It puts restrictions on the kinds of things we could do, and but the weird thing about symmetry is that for instance we would think that things should be isotropic. That means it should be invariant under rotations, but here we are on earth and there is always a preferred direction, and that is the direction due to gravity. So, quite often we are actually, even though the underlying force is the 1 upon r, rather the potential is 1 upon r, we are in a situation where there is a preferred direction. Then you may say, okay, fine, let me not think about the earth, let us take the whole solar system, but even there if you think about it, earth is moving in a plane. So, again there is a preferred direction, if you wish, which is the normal to the plane. So, it appears that all the time we are in a situation where there is a symmetry, but it is not obvious to us, and this is sometimes called hidden symmetry, or more commonly called broken symmetry. Okay. So, one may wonder, do we need to really worry about symmetry, and the answer is yes, because as I mentioned some time back, it puts lot of restrictions. So, what we will do is we will start with Newton's equations, which we know very well, and ask what are the symmetries, or the precise statement for an equation is the invariances of the equation, and we will see that certain nice structures will emerge, and then we can map it into some problem in mathematics called group theory, and then again we can come back to physics. So, what we are going to do first today is to discuss the invariances of Newton's equations In fact, Newton's first law already picks out a preferred set of observers. These are observers who will agree on the forces. In fact, the classic thing is to imagine yourself in a train moving with a uniform velocity, and then Newton's first law will tell you that you will agree with the forces acting on some other particle with a person standing on the railway platform, because okay, that is one example. But the minute the train either accelerates or decelerates, you start feeling forces, and then you have to add to make Newton's law work. What you do is you add what are called pseudo forces. Okay. Of course, more a dramatic example is that of a rotating system. If you are in a merry-go-round or something like that, there you will so the key point here is that we will look for observers for who agree on the forces. Okay. So, we will give them a name, we will call these people observers, inertial observers. Okay. And the question we will ask is what characterizes these observers, and every observer, what do? They will assign a coordinate or whatever x, y, z, and some time to an event, to something. Okay. So, if you have 2 observers, they will assign 4 different numbers to something, and the question is how will they be related, given the fact that we have said that they will agree on these forces. So, what we will start out with is the obvious situation is to consider a thing where a particle which is being observed or whatever has no force acting on it. Okay. So, the equation, so that's so the for a particle that has no force acting on it, the equation of motion, so this will be a standard short form, EOM for equation of motion, is nothing but could have written a mass out here, which is what you would have written, but I can just get rid of it. So, this is the equation, and so this is something. So, let's choose a situation where this is observer 1, and let us say observer 2 assigns coordinates x prime, y prime, z prime, t prime to the particle, and this they do not even have to agree on time, and the equation of no force for this person would be this. So, now what we would like to ask is what is the most general relationship between x prime, y prime, z prime and t prime, and x, y, z and t, which is the one due to. Okay. So, they are both assumed to be inertial observers, and we have decided that there is no force. So, this is the equation they would write. Okay. It has to be t prime. Okay. So, let us sort of do it in parts. So, the invariances or the relationship. So, first thing we could do is translations. Okay. So, x and x prime could differ by some constant. So, more generally we could write something like x prime equal to x plus some constant. Okay. But again they need not even agree on some t naught. So, this is translation in space and this is translation in time. Okay. There can be something more general, we could have rotations as well. In other words, x prime, okay, let us put some index structure to this. X prime I is some matrix R I j x j, again Einstein summation, where R is a rotation matrix. So, this satisfies R dot R transpose is identity. Okay. And if you notice, I am sort of preserving something out here. I am saying that look, I is an upper index out here, I keep it as an upper index out here, and j is a lower index, and you can, so I and this j is an upper index. So, the rule will be, the Einstein summation rule always through this course will be that we sum over one upper and one lower index. Okay. And so, and it should be, so this j is a repeated index, while I is what is called a free index. Okay. So, this is how it is going to be, and you can ask, can I end up with a situation with 2 lower indices being the same? The answer is you are doing something wrong, for instance. Okay. So, we will get back to what this thing is. So, we know that we could write this rotation matrix, you could choose how many parameters are there in this rotation matrix. Just one, okay. Anyone else? So it has three parameters. One possible choice is something called Euler angles. Okay, so far we have got 1, 2, 3, 4 plus 3, 7 parameters, and now comes the interesting part, which we will call Galilean boosts. Okay, which is the following. So this is exactly the coordinates which would ut and t prime equal to t. Okay, so this just tells you that this observer is moving with some velocity u with respect to observer 2 is moving with respect to observer 1 with some constant velocity u. Okay, and it is not hard to check that since this involves two derivatives, it still satisfies this equation. Okay. So now this is again 3 more parameters. In fact, there are quite a few more if the particle were having no forces. For instance, there is nothing which sets the scale of x or nothing which sets the scale of time. Okay. But we know that once you apply forces, when you go to a situation with forces, you get a scale for x, you get a scale for time. So those kind of scale invariances, which is actually the symmetries or the invariances of Newton's equations without a force, is much larger than what I have written. But I am going to keep in mind that there will be forces which introduce scales in this thing. So for instance, the m which we wrote here, when there is a force acting on it, you cannot. Okay. So what we see, so I will restrict myself to only these 3 things, and so now you can see that there are 10 parameters worth, and of course if 2 arbitrary observers are there, they could be, it need not be just one of these things, it can be the most general thing which could relate these 2 things. So in other words, we could write something like x prime, so this would be the most general sort of thing, I equal to r I j upper Okay. So this is the most general thing, and these set of transformations are called Galilean transformations. So I started out here with a particle with no force acting on it, but you could do the following thing. You can take Schrodinger's equation, take the time dependent Schrodinger equation and ask yourself the same question. Okay. But just bear in mind that in quantum mechanics the wave function need not go back to itself, there is a phase freedom, so you can use that phase degree of freedom. So there is a nice exercise which is the following. So I will keep giving you exercises, and I expect you to go back and play with it, because that is the only way you can sort of learn and understand these things. So the exercise is the following. So take a different equation, in this case it is I h bar d psi x and t by dt equal to, say, a free particle. So let us just write it, p square upon 2m acting on and ask the same question. Ask when two different persons, two observers will get the same, will agree on this equation. Okay. So the point here is that, so this would be observer 1, observer 2 would write out something like this. So you can replace P with del square the Laplacian minus of the Laplacian with some h bars put in there, but okay. So now you need to work out what is the map, and really all you need to do is to realize that psi of x prime, let us put even a prime out here because it even need not be the same function, should be equal to up to some phase, which you have to fix by the way. Now comes the amazing thing. The amazing thing is, it looks like we are doing a completely different equation, right? You go ahead and you will discover the same thing. So the invariances of the Schrodinger equation is the same as Newton's laws. Now you can even ask, let us look at, there are equations which say how paper burns, for instance. There are some beautiful exponents called the Kardar-Parisi-Zhang exponents which come from that, how paper burns. Go ahead and work out its invariances, and lo and behold again you will discover Galilean transformations. Take Navier-Stokes equation which tells you how a fluid flows. All of them give this thing. Okay. But intuitively at the end of the day it should agree. Why? Why is it? Why should it agree? Suppose it didn't agree. Suppose let us assume that fluid flow was such that it did not respect this thing, then we can think of we can use the fluid flow to say, for instance, distinguish between, we might be able to measure velocity, there might be some absolute velocity or something, because there are two different setups which differ in some way, and then these two observers can actually differentiate something. So here we took a particle, there you could, I mean instead we can take a fluid and see what is happening. But of course we also know that fluid flow, it comes back from taking many particles and the underlying equation is still the same. So there is something special about the Galilean transformations. There are 10 parameters out here. Okay. And the surprise here is, so we know one more set of equations which is Maxwell's equations, and you can ask, what are the invariances of Maxwell's equations? And this is something we will work out maybe later today or maybe in the next lecture, because I just want to focus on this set of transformations and ask certain questions about this. This P, yeah, P is an operator now in quantum mechanics. So in this thing here it would be, the operator would be d by so P would be, let us write it this way, Pi will be I. So maybe I should put a prime here if you want, if you are comfortable with that, and 1 without this. Okay. So each person will write the equation in their frame, they do not care about what someone else is doing. The question we are asking is how would these two things be related? They should be related. So this is an exercise for you to do. It's a lot of fun fixing the phase, and actually after you finish doing this thing and you get the phase, what you find is that the phase has a very nice interpretation. Said, hey, I could have written it before even I started, you know. So but that's why I will not do it. So right now what we did was we took two observers and we worked out how these things get related. But the key is we do not have to restrict ourselves to two observers, there can be millions of observers. Okay. But we will simplify things, we will take only 3 different observers, we will call them 1, 2 and 3. Observer 1, observer 2, we already have 2 of them, and we have a third observer, and let us say that as before x and t, x prime, t prime, and the number of primes are increasing, so we will put a double prime out here. So, these are the coordinates chosen by observer 1, 2 and 3. And what have we said that x prime is, so let us draw the arrow this way. So, this you get x prime as a function, rather this is the way it goes. So, the way this equation that we have out here star tells you how to relate get x prime and t prime in terms of x and t. Okay. Obviously, there is a opposite one which we should call star inverse in some ways, but the neat thing is there is nothing special out here. This the inverse transformation also should have the same form, with except that the 10 parameters that we see out here are different. Okay. So, you can work out. So, exercise again for you to work out what is the inverse. Okay. Now, what about 2 and 3? There has to be a similar transformation. Okay. So, let us sort of maybe there is another way of doing this. Let's say that this takes, let's put all the parameters and say that this takes observer 1 to 2. I will replace Roman these things with the normal Hindu Arabic numerals out here. R1 goes to 2 for the parameter, this is 1 goes to 2, 1 goes to 2, same thing out here. Okay. So, this is the change, this is what I would do. So, the parameters here, so let us just put all the parameters and just call it P for parameters, 1 goes to 2. Similarly, here there should be P 2 goes to 3, and this will be P 2 goes to 1. Similarly, we will have P 3 goes to 2. But now comes the neat thing, 1 and 3 are also inertial observers, they should also agree with each other. So, there will be another set similar transformation with just the parameters changing, and we will just call this P 1 goes to 3. There will be an inverse. So, let us leave this, but the most important thing is there are two ways I could have gone. I can go from here to here to here, but I can also go directly. So, we get a very important property. It says that P 1 to 3 is equal to P 1 to 2 composed with P 2 to 3. It just means follow the arrows, and please remember that because of the way mathematical operations are done, the first one comes here and the other one comes here. This is very simple. So, physics tells you that this has to be true. Okay. So, we will just call this a composition rule. Okay. And there is also the other thing which I just mentioned, P 2 to 1 should be equal to the inverse of P 1 to 2. Okay. So, now comes the, so it is you can go back to the equation star and keep putting these 1 to 2 labels and 2 to 3, and you can work out what is the how these set of parameters get labeled. Okay. It's again another exercise which will come in your assignment, where you actually should work out how the parameters precisely change. Okay. It's not like it's a product of the parameters, it's a complicated one, because I am not doing, if you just did 2 translations, of course they add up. Okay. Or if we did 2 boosts together, of course they add up with the vector addition rule. But what I am saying here is take the most general thing, do not assume anything about these things. Okay. And of course, there is a trivial one, 1 goes to 1, which is doing nothing, which we will call the identity. Actually these three composition rules, these three rules underlie something in mathematics called a group. There is just one more property which you need, which would require a fourth one which I haven't. So again the last bit is if there was a fourth one, and let us just call it so P41. So I am not drawing the other box, I am just writing it out. P41 should be P1 goes to 2, say, composed with P2 goes to 3, composed with P3 goes to 2. Okay. Now the thing is, the answer should not matter whether I first do this composition or if I do this composition. And what is this such a property called? Associativity. 3 goes to 4, thank you. So 1 goes to 2, so the order should not matter. Thank you, it is 1 to 4, thanks. Okay. So this should not depend on the bracket, so there is the obvious property, but we should. Okay. So the amazing thing is that these 4, so let us call them 1, 2, 3 and 4, these 4 properties define a group. This mathematical, this thing will give a formal definition later, and in this instance with this rule we get here okay, because it is obtained from Galilean transformations. Just one more point is that here for instance I could have put, even if scales are fixed, I could I mean I did not put a minus sign here, this would remain for instance this would correspond to reversing sign. Similarly I could put a minus sign out here also. Okay, I sort of been very loose, but usually in terms of time we always agree in terms of how time would increase. So you want the observers to all agree as to what is the positive direction of time, so that one does not usually consider that, but we do consider situations where you would put a minus sign out here, but that is actually more or less, this was the condition that we had put on this thing, so that will allow for this thing. Okay. So this is the example of the Galilean group. So you can see that the simple idea that we started out with, that we expect inertial observers to agree on their forces, led us to something which is far more general than the equation we started out with. Okay. So are there any questions? Okay. So what we will do now is to gear ourselves towards asking the same question for Maxwell's equations, and what we will find is that you get something different. Okay. So that is the first instance where there is a conflict, and this is a theoretical conflict which can be only resolved by experiment. Okay. And like I said, there are enough examples where this holds, and we have only one sort of set of equations for which it does not hold. So you may think, this is the worst guy, I mean I forget about it, but there, as I mentioned to you, light is somewhat different. I mean electromagnetic radiation is also different. It is the only example where we have of a velocity dependent force which is also conservative, which already sort of tells you that there is something special about it. Okay. But at this point we are just going to be very naive, we are going to say fine, let us ask what are the invariances of Maxwell's equations. So in order to do that, it turns out that Maxwell's equations in SI units are not the best suited for getting its invariances, and so we will get to writing it in rewrite Maxwell's equations in a slightly different ME stands for Maxwell's equations. So let me write it out for once in SI units. So, I am writing it in free space. Hopefully, there are no sign errors. So you can see that I mean most of you would be used to writing these things on the right hand side, but there is a sign error here, and this should be minus. Okay. So there is a difference between the top line and the bottom line. The top line has sources. So this is the charge density and this is the current density, while these are just this hold independent of whether there are sources or not. These are the source free Maxwell's equations, and these are the ones with sources. Okay. Yes. Where? Here. It's 1 by
just mu naught epsilon
here. Okay, good. Thank you. So what we will do now is to change units. We go to what are called Gaussian units. So this is called Gaussian units. Standard in any E&M book will have it at least in the appendix. Okay, but I will tell you how it works. So the first, there are only two steps we need to do really. The first step is to write Coulomb's law for a so this is a force between two charges. So okay. So R12 here is the vector which connects 1 and 2. Okay. So this k is this constant. So k is equal to 1 by 4 pi epsilon naught in SI units. In Gaussian units, k is equal to 1 in Gaussian units. In SI units, charge was measured in coulombs, but in Gaussian units is measured in stat coulombs. Okay. So this is the first step. The second bit is that what we will see later is that both electric fields and magnetic fields can mix in some ways, and so you need both of them to be measured in the same units, and that is still not true. So what you do is you make the replacement. I am just making it as a replacement, but you can make it formal. But okay, wherever you see B you put. Okay. And the way to see that this is correct is to just use something very elementary, which is the Lorentz Force Law, which in SI units was just Q into V cross B plus E. Okay, where C here is the speed of light. Okay. So if you make this change, that is to put wherever you see B, you put B upon C. Now V upon C is dimensionless, so you can see that E and B are being measured in the same things. Okay. So now we can go back to this equation and start modifying things to make it look like the same thing. So what I am going to do now is to use the same equations, but I will just input these things. Now you can see that there is a simple trick of going from this to this by just noticing that wherever I see epsilon naught, I just put 1 by 4 pi. Okay. So I see an epsilon naught out here. So what is it I do? I go ahead and put 1 by 4 pi. So, I get a 4 pi. This equation I just put a 1 upon c. Okay. Yeah. So, just one more thing which we need is c naught. C is nothing but 1 by square root of mu naught epsilon naught. Okay. So, instead of doing various things, all I can do here is to replace this with 1 by c square. But we already know that epsilon naught should be 4 pi. So, this would just tell you that mu naught square, okay, mu naught epsilon naught equal to 1 by c square, but epsilon naught is 1 by 4 pi. So, this implies that mu naught is 4 pi upon c square. No, let me use the other color. And nothing needs to be done here, 1 by c, but here I need to do a one more 1 by c. Okay. So, you can see that what I have done is it just it looks like the changes are sort of very simple, but let us see what we get. So, I am going to now rewrite the whole set of equations. Okay. So, now you can see out here I can just cancel one factor of c out here, and then so I get used up too much space. So, let us just do that. Okay. So, this is Maxwell's equations. So, let me use this color to separate these things. So, this is Maxwell's equations in Gaussian units. There are already nice things that you see out here. For instance, we look out here, we see that wherever t is coming, it is coming in the combination C t. Okay. So, we can replace C t with something which I will just write as x naught. I will define this combination x naught. Okay. Then c disappears from this equation and out here. There is only one factor of c which remains out here, but actually both rho and j satisfy an equation that is a consistency condition, if you wish, of Maxwell's equations. And what is that called? The continuity equation. So, let us look at the, so let us try to understand that factor of c. Okay. So, you have the equation of continuity, which says that d rho by dt plus okay. But if you wanted to write in terms of x naught, you have to put a 1 upon c out here. So, what you see in a nice manner is that either I could write j upon c, or I could multiply this guy with I could either divide j by c or you multiply rho with c. I mean you have that freedom, but in some sense there is. So, you can see that this becomes now so now we are sort of almost ready to work out what are the invariances of Maxwell's equations, and in principle I could do it at this point, but there is something we could do which is analogous to what we would do when we looked at an equation like this. When we look at an equation like this, we say that the left hand side is a vector, but what about the right hand side? M is taken to be a vector scalar and A is a vector. So, product of a scalar and a vector is another vector. So, this equation is a vector equation. In fact, this is true about all these equations. Okay. So, this is the first rather this equation and these two are vector equations, while these are scalar equations. So, if you want to count this thing, you have 10 such equations, and so the advantage of writing it in this form is the fact that your rotational invariance is manifest. In ME as well as Newton's equations. Okay. So, one obvious invariance of Maxwell's equations is there even before we did anything, even before going to Gaussian units. It has to do with the fact that these are all nice equations under rotation. So, we know how they transform, but we also, what about translations? You can see that there is no explicit dependence on time or spatial coordinates in any of these equations. Okay. So, translational invariance in space as well as time so it only leaves only thing we need to check is it invariant under Galilean boosts. So, an invariance okay. So, we will see that it is not, but we will work it out explicitly next lecture, but what we will do now is to use a thought experiment to show that it cannot be so. Okay. And I will make use of the fact that the Lorentz Force Law is velocity dependent. So, consider observer 1 who sees, let us say that this is a charged particle and I am observer 1, I am standing out here, and let us say that we are in a region of a constant magnetic field. Okay. So, observer 1 is at sees the charged particle at rest and says there is no force acting on it. What about observer 2? Okay. Let us take observer 2 to be moving with uniform velocity. That means with there is a Galilean boost in a frame, it has a Galilean boost. So, it is moving with uniform velocity with respect to this. So, suppose he is moving in this direction, he would perceive this stationary object for me as if it were moving with a constant velocity in the other direction. So, now he would perceive the following thing, that there is a force acting on it, and what is the force? That is just the, it is a charge, there is a magnetic field, and there will be a force which is u cross b acting on it. Okay. But now that really conflicts with what we saw earlier, that these two inertial observers should agree on the fact that there is no force acting on this thing. Okay. And so, the resolution to this is that the resolution to the thought experiment is very simple, is that E. So, we are in a situation where E is 0 and B is non-zero in frame 1. In frame 2, you would see that E prime is not 0 and B prime is not 0. Okay. In other words, what happens is that what was a situation with only E B magnetic field in here becomes mapped to a situation where B and E fields mix. So, in some sense, well, you may think that this does not conflict with Galilean boosts, okay, but the answer is that it does, because we have to prove that these equations are invariant. So, what we will do in the next lecture is to rewrite these equations in a manner where it would be invariant under something larger, something different. So, we will find that Galilean boosts are replaced by something called Lorenz boosts. Okay. So, our goal will be to work out what Lorenz boosts are, but what I will do it in an easy manner, just as the way we define rotation group as R transpose R equal to identity. We will see that there is a similar representation of Lorenz boosts, but the key point here is that already you start seeing here that x0 which we defined out here is now time is being measured in units of length. So, it is exactly what we did for making E and B to be measured by the same thing. So, it kind of tells you that there can be a situation, so where both x0 mixes or time mixes with the spatial coordinates. In particular, this particular thing we always thought that there was something universal about time. Time just played a spectator role in this whole thing, and we will find something much more complicated than this. But there will be exactly 3 Lorenz boosts, just as we had 3 Galilean boosts. Again, because it is the invariance of Maxwell's equations, it will satisfy a group property, okay, and we will call that group the Lorenz group. Okay. But now the thing is, it looks strange. Now there is a problem. There are some sets of objects which have a symmetry group, which is the Galilean group, and another set of objects which have a Lorenz group. Obviously, one of them should get corrected, and what experiment tells you that it is the Galilean boosts which get corrected. Okay. But there is also a beautiful mathematical structure which relates the Galilean group to the Lorenz group, and it is called contraction. Okay. So, the contraction of the Lorenz group actually gives you the Galilean group. That is a mathematical statement, but the physical statement is that it is not as if special theory of relativity proves Newton's equations are wrong. It just says that it extends the validity of Newton's equations to a much larger regime, to velocities where velocities become very, very large. Okay. So, it is not that Newton was wrong, it is just that the validity of his equations are much more limited. So, science also always progresses in this fashion. You never go there and there is nothing radical where you go wipe out everything that was known to mankind before. That is total nonsense. What happens is that you add something to what was existing there. Okay. So, when you become in the future scientists or doing something, be sure to see that your results are compatible with what people have done. Even the people in the past are not complete idiots. They are, but the point is that there is some method. Okay, and this is called the scientific method, and so this is we will see this captured in this simple example for which we know the resolution, but we will in the future go to situations where things are where we do not know the answers, and there is this condition which you had imposed, that there should be some limiting thing which you by which you require earlier results. Okay, thank you.